Everything around you depends on invisible rules you never think about. Now imagine this. Those rules don't break, they don't bend, they change, no explosion, no warning, just a universe that suddenly stops working the way it used to. We treat the laws of physics as permanent, like they're baked into reality itself. But modern physics quietly admits something uncomfortable. There's no guarantee they always were, or always will be. The forces holding atoms together rely on numbers so precise that a microscopic change would make stars impossible, chemistry unstable, and life completely unviable. And here's the disturbing part. There are real theories suggesting those numbers might not be fixed at all. In this video, we're going to break down how the laws of physics could suddenly stop working, not slowly, not dramatically, but instantly. And why, if it ever happens, there would be no time to react, no way to survive, and no one left to understand what went wrong. To understand what that means, we first need a reminder. Our laws of physics aren't divine commandments. They are patterns we've observed, measured, and codified into a mathematical language. They are the grammar of reality. At their heart are the fundamental constants, numbers like c, the speed of light, g, the gravitational constant, and alpha, the fine structure constant. These aren't just numbers. They are the universe's tuning knobs. Alongside them are symmetries, profound principles that demand the conservation of energy, momentum, and charge. For centuries, across billions of experiments and observations, from the smallest subatomic scales to the grandest cosmic structures, these rules have held firm. They are the bedrock of our understanding, the foundation upon which all of technology and science is built. But we know from experience that nature can change its rules. We see it every day. When water freezes into ice, its properties transform completely. A liquid that flows becomes a rigid solid. When a piece of iron cools below a certain temperature, it can suddenly become a magnet, gaining a north and south pole where none existed before. In physics, these are called phase transitions, and they are governed by the breaking of symmetries. In the liquid state, water molecules are oriented randomly, a high degree of symmetry. When it freezes, they lock into a crystal lattice, breaking that randomness. A new, more structured set of rules appears from the same deeper equations of electromagnetism. Could the universe itself be in just one of many possible phases? Our best cosmological models suggest the early universe was a radically different place. In its first moments, it was an unimaginably hot, dense plasma, where the fundamental forces we see today, electromagnetism, the weak and strong nuclear forces, may have been unified into a single symmetric superforce. As the universe expanded and cooled, it likely underwent a series of dramatic phase transitions. Symmetries shattered. A single unified rule could have fractured into the distinct local rules that govern our cosmos now. It's like a perfect, clear pane of glass suddenly shattering, creating a complex web of cracks and patterns. The glass is the same, but its expressed structure is forever changed. This idea opens a fascinating possibility. Some theories propose that the fundamental constants aren't truly constant everywhere and for all time. Perhaps they vary over vast cosmic distances or evolve slowly over billions of years. So far, the evidence is against it. Our measurements of distant quasars and the cosmic microwave background show that any such variation must be incredibly small, within extremely tight limits. But small is not zero. Tiny, imperceptible drifts could still be hiding in the margins of our measurement uncertainties, a signal buried in the noise, detectable only by our most ultra-precise instruments. If the fine structure constant, which governs the strength of light and matter interactions, were to change by just one part in a quadrillion, the consequences wouldn't be apocalyptic. There would be no explosions. Instead, the light from distant stars, analyzed through spectroscopy, would show a subtle collective twitch in its spectral lines. Our global positioning system, which relies on perfectly synchronized atomic clocks, would start accumulating errors, requiring new, unexplained corrections. Particle accelerators, smashing protons together, would report persistent anomalies in their data, results that just don't quite fit the standard model. It wouldn't be a catastrophe, but a deepening, maddening mystery. Then there's the far more dramatic and unsettling idea of false vacuum decay. This theory speculates that the vacuum of our universe, the baseline lowest energy state, isn't actually the true bottom. We could be living in a false vacuum, a metastable state, like a ball resting in a small dip on a hillside, rather than in the deep valley below. Quantum mechanics allows for the possibility that a bubble of the truer vacuum could spontaneously appear somewhere in the cosmos. This bubble would expand at nearly the speed of light, and inside it, the fundamental laws of physics would be different. Particle masses, force strengths, even the stability of atoms could be rewritten. We would not see it coming. There would be no warning, no signal that could outrun the bubble itself. One moment, our familiar equations work perfectly. The next, they describe a universe that no longer exists where we are. The very fabric of reality would be rewoven into something unrecognizable. It's a terrifying thought experiment, but it's also very, very unlikely. The fact that our universe has existed for nearly 14 billion years without such a catastrophe suggests our vacuum is remarkably stable, if not truly fundamental. A less dramatic but more plausible path for new physics involves hidden sectors. We know our standard model is incomplete. It doesn't account for dark matter or dark energy. What if there are entire families of particles and forces that exist alongside our own, interacting with us only very weakly, perhaps only through gravity? If a field in this dark sector were to shift its value or couple just a tiny bit stronger to our world overnight, the effects would be subtle. We might observe unexpected changes in galactic motions or tiny anomalous accelerations in satellite trajectories. The first signs would be whispers in our gravitational data, at first dismissed as errors, but eventually becoming undeniable. Sometimes, new laws aren't fundamental at all, but emergent. Inside certain materials, the collective behavior of countless electrons can be described as if they were entirely new particles, called quasi-particles, with their own unique masses, charges, and rules of interaction. The underlying law, quantum electrodynamics, hasn't changed, but a new effective law has emerged from complexity. What if space-time itself is an emergent phenomenon? If it has deeper hidden layers, a phase change in that underlying structure could alter the effective laws of gravity and quantum mechanics that we experience. Ultimately, our confidence in the laws of physics rests on their symmetries. The work of Emmy Noether taught us one of the most profound truths in science. For every continuous symmetry in nature, there is a corresponding, conserved quantity. Symmetry in time, the fact that the laws are the same today as they were yesterday, guarantees that energy is conserved. Symmetry in space guarantees momentum is conserved. These symmetries are the backbone of predictability. But if a fundamental symmetry were to break, even slightly, then conservation itself could bend. Perhaps locally, perhaps briefly, but in a way we could hope to detect. So, how would we actually know if something had changed? The first alerts would come from a global network of detectors. Our most precise atomic clocks, scattered across the globe, would begin to desynchronize in a correlated pattern that couldn't be explained by local effects. Spectral lines from thousands of distant quasars, observed by different telescopes, would all shift in unison. The faint hum of the gravitational wave background might gain a new, unexpected note, a new tone in the symphony of the cosmos. The key would be correlation, the same anomaly appearing everywhere, at the same time. Our deep space probes, Voyager, Parker Solar Probe, Juno, are perfect, isolated witnesses. Their trajectories are modeled with breathtaking precision. If one of them experienced a tiny, unmodeled acceleration or a persistent drift in its communication frequency, engineers would first check for mundane causes. But if, after subtracting every thermal effect, every solar wind gust, and every relativistic correction, a residual anomaly remained, and worse, if it appeared on other spacecraft too, it could be the first hint of new physics poking through the seams of our models. Meanwhile, in particle colliders like the LHC, physicists would be tearing their hair out. The probability of certain particle interactions, known as cross-sections, would begin to deviate from predictions. At first, it would be a few standard deviations, dismissed as a statistical fluke. But the anomalies would refuse to average away. They would repeat across different detectors, at different collision energies, and in labs on different continents. Eventually, the weight of evidence would become overwhelming. Statistics would surrender to a new reality. Would your daily life change overnight? Almost certainly not. Most of these scenarios begin as precision headaches for a small community of scientists and engineers. Your lights would still switch on. Your car would still start. Your coffee would still boil, though a physicist might fret that its boiling point had shifted by a millionth of a degree. The initial impact is on our knowledge, not our existence. And the first, most powerful response would be skepticism. Could it be us? Is it a subtle calibration bias in a new instrument? A software bug in the data analysis pipeline? An unnoticed systematic effect from a solar flare? The history of science is littered with mirages, discoveries that turned out to be instrumental artifacts. Extraordinary claims demand faultless instruments, independent cross-checks, and merciless adversarial replication by competing labs. The burden of proof would be immense. Then there's the provocative, almost philosophical idea. What if our reality is a computation, a grand simulation? In that case, a change in the laws of physics could be nothing more than a software patch, a parameter tweak by the system's operators. It's a compelling story device, a fascinating lens for science fiction. But it remains just that, a story. Unless such a hypothesis can make a unique, testable prediction about the world, it isn't science. So, we hedge our certainty with humility. Our laws are not absolute truth. They are models that have, so far, never failed us within their tested domains. If the universe shows us that a law can budge, it doesn't mean our map is wrong, only that it's incomplete. We wouldn't abandon the map. We would work tirelessly to expand it, to draw the new territory that was just revealed. What should we do now, in the quiet moments before any hiccup? We do what science has always done. We build better clocks, longer baselines for our telescopes, and deeper cosmic surveys. We share our data openly and globally. We hunt for the tiniest drift with relentless patience. If the universe intends to show us a surprise, we will have earned the right to understand it. The odds of a sudden break are tiny, but the value of looking is enormous. Our certainty is not the point, our curiosity is. So we watch the sky, we watch our instruments, and we watch the laws themselves.